If Fire told me, come on up, we'll celebrate your birthday with a party, and then I didn't know about the talk. Anyway, so here's my title cover. That's the South Pole Telescope. I'm going to be talking about cosmic microwave background measurements. That is actually at the South Pole, well, 1 kilometer away from the South Pole. And I noted in the schedule, first of all, I'm honored to be asked to come and speak at this series. And I noticed Lyman Page, who actually chaired this Gruber Prize, is giving a talk in about a month. So some of the things I thought Lyman's likely to talk about, because we had to do joint talks for these things, I left out. And there's still too much in there. So if you want to stop me, it's fine. You can pace this talk if you'd like. But I thought I'd start somewhere. And where do you start with cosmic microwave background? Start with Penzias and Wilson. So it was 50 years ago last year. That marked the 50-year anniversary of the discovery of this cosmic microwave background, this relic light from the Big Bang. And it was these two guys, Bob Wilson and Arnold Penzias, who did this. And I have a hard time resisting these jokes, but I always like to say this shows you that all microwave background telescopes look weird and that half of all the cosmologists are bald. But this I like to show this because it was really an amazing event. They discovered and made this discovery not because they were out looking for it, but because they built a really sensitive receiver. And you guys have probably learned about receivers and radio techniques in this series. And when you do something that's that much better than what preceded it, you tend to get new results. They also had an incredibly well controlled antenna, so they could control systematics and things like that. So when they got a funny looking signal, excess noise, they didn't just say, well, it's this. And then the third thing they did is when they had something they didn't understand, they persevered for a couple of years to figure out what it might be, rather than just saying, oh, there's some excess noise and whatever. And the results, of course, they discovered this incredible glowing universe in the microwaves, which is the cosmic microwave background, every direction you look. And of course, it had enormous impact on cosmology and our understanding of the universe, because it really was the smoking evidence for a very hot Big Bang, or a hot beginning, hot, dense beginning for the universe. And the other thing I like to point out is things have moved on in 50 years, and you can actually do this experiment. Freshmen at the University of Chicago, with this little receiver we use, go out and do this experiment where they measure how much radiation they're getting as a function of air mass and extrapolate the zero air mass, and you can detect the cosmic microwave background. So that's where we're going. Nevertheless, so it's bright, it's strong. If you have your TV turned to noise, some fraction of that noise is the cosmic microwave background being picked up. But it's very isotropic. And so when it was discovered, of course, the thing was then, cool, right? We can go out and we can look at the early universe. What does it look like? And for 30 years, wherever direction you looked, it looked pretty much the same. It was very, very isotropic. And it wasn't until 1992, almost 30 years later, that the COBE satellite, with what they call the differential microwave radiometer, measuring the differences between patches on skies as this satellite's moving around, detected that it wasn't the same in all directions. Now this is processed because actually the galaxy would be showing up, but this is trying to show a sphere surrounding you, the whole sky, where the monopoles are moved, the galaxies are moved, and this fluctuation is this changes in the intensity of cosmic microwave background. The other thing that satellite had was called FIRAS, far infrared, help me out, Giles, far infrared astronomical spectrograph or something. And they measured this spectrum, so this is frequency and intensity, and you'll recognize that as a black body curve. And what they always like to point out, or I do, this was done in 1992, is that the data points from the satellite, those are not 1 sigma errors, those are 400 sigma errors. So it's very precise measurement showing that the cosmic microwave background is beautiful black body spectrum. Easy physics, simple physics, thermal equilibrium, no funny energy injection. That's good. And this result with that precision has held up now, has not been improved upon. A few data points at long and wavelengths, but hasn't been improved upon. There's an experiment trying to do that. So the fact that it's so smooth in every direction, if you're not used to this field, ought to upset you. because we're looking at light that came, from the early universe, 14 billion years one way. You look at the light from another way, it's just reaching you halfway in between, and it's synced up. It's synced up to a part in 100,000. So what caused that? There were other problems. When you didn't see any isotropy for 30 years, people realized that there has to be isotropy. There has to be some sort of structure formation happening at this time when we see this light, because you need to seed all the structure. And so two things came out of the fact that there was no detection. One was you needed some cold, dark matter that didn't interact with light to start structure formation going. So this whole idea of cold, dark matter started then. Not just dark matter to hold galaxies together, but cold, something in the early universe. And that you needed something to synchronize things. So this was this idea that you had in the very early universe, fraction of a second, this ginormous inflationary event where space was moving out due to some false energy state or a very high energy state, expanding at an enormous rate, adiabatically cool things down to the ground state immediately, but then you have quantum fluctuations, and those quantum fluctuations are being stretched out to astronomical signals and locked in. And so there's this mechanism called inflation. It creates this enormous isotropy, seeds all the structure through quantum fluctuations for the universe, and eventually it stops. The inflaton potential, whatever, decays, and we get particles, and here we are to talk about it today. So, you've heard we are star stuff. According to this theory, we are quantum fluctuations. All right, we're amplified quantum fluctuations. So, cool. That's pretty cool. They got the Nobel Prize, of course, 2006, for these two parts of the experiment. And it says when you look at this, what you're seeing are quantum fields. When we look at the cosmic microwave background, we're looking at quantum fields, stretched out to astronomical, as large as the observable universe and presumably beyond. So kind of neat. Once this was out there, then finally, after 30 years, we knew the level, but it was only measured in these very large angular scales. COBE didn't have the high angular resolution, so 7-degree scales. And you'd like to see what does it look like on smaller scales. Even 7 degrees, looking back that far in time, subtends an angle bigger than the horizon, bigger than the light travel time of the universe at that point. So once the mark was set, then there were lots of experiments to go out and measure finer angular scales. My experiment was DAISY. Boomerang is you may have heard of that. In fact, all these. You notice the first talk was on the secret weapon interferometry. We used that secret weapon. My whole background was interferometry, but not for what you heard. We used it for extreme stability, and because we wanted to get down these low signals and characterize it. So the DAISY went well. I'm not going to show you the results from this. Lyman Page did TOCO. DAISY, TOCO, Boomerang, Maximum measured these peaks, which I'll show you in a second. Akbar came a little later. It was great times. And this is a plot from that period a little later from a review article by Wayne Hu and Scott Dodelson. And before I explain this plot, this is amplitude of a variance, so it just means statistical amplitude, versus multipole. So what does that mean? And so you're used to, you're a physicist, used to quantum mechanics. You have your spherical harmonics. The amplitude we're just talking about is the variance and the ALMs for a given multipole, right? And so this is a little animation Clem Pryke put together saying if this is your angular power spectrum, and you can see a red line should start coming across here, this is a realization. And the reason we do that is, of course, no theory predicts where you're going to have hot or cold spots, but they will predict the statistics of the power spectrum, right? So we use these YLMs to do that. Yes?
How do you determine the multipole?
Well, the multipoles, so we make maps of the sky. I'll show you that in a bit, but we make maps of the sky. Once you have a map of the sky, you can Fourier transform effectively into a spherical harmonic basis. And then you take the ALMs, and what you put on this chart is the variance for every multipole. And if you don't measure the whole sky, that means...
So it's the spatial...
You make maps? Right, that's right. So if you're used to interferometry, you're constantly going back and forth between maps and power spectra. But I wanted to make sure you're comfortable with this a little bit, because it keeps showing up. So this is the data. They did it in such a way, because they're reviewing lots of things, where the darker the box, the more significant the measurement. And you can see the darker boxes start to trace out something. And this line is this fit, kind of a best fit line for what's now called a lambda cold dark matter, or lambda CDM model. Lambda is Einstein's cosmological constant, right? Which, dark energy and the supernova, this had just come out a few years before that. And inflation, the amazing thing about inflation is it predicts that you should have one peak, which subtends an angle, as the mode on the sky is about an angle about the horizon, and then you should see harmonics. And these harmonic structures of this curve essentially reflect the dynamics in the early universe, the dynamics in that gas, sound waves for the most part. So you have gravity from dark matter, you've got all the gases ionized, so you have photons interacting with electrons, giving you pressure. And this model, this very simple cosmological model, and this very simple gas, remember it's a 3-degree beautiful black body, has these very little variations that we can see, part in 10 to the 5 or less, and you should see this power spectrum. That model for our universe from inflation has stood up to the present day. Every now and then there's chinks in the armor. We had a crisis in the 90s because if you have inflation going on, then any large-scale warps or curvature in the universe should be completely wiped out through this inflation. But we were getting that the universe was not flat. And it turned out dark energy solved that. When we had dark energy or this supernova expansion, all of a sudden the universe is flat. Now we measure it's flat to within 1%. Inflation keeps somehow winning, fitting the data. It's got to break at some point, but we'll see. So that's kind of the background. Let me jump ahead a little bit. Well, go back to the kind of why we're doing any of this. So this is this. I put this up thinking most of you probably have seen this figure. In fact, I've used it on this computer so much you can see it starting to fade. But it just kind of has it all there, right? So the idea is that, here's time, that you have a time going on, you have this rapid, superluminal expansion of space, and then somehow inflation ends. It ends, things start to slow down, decelerate, things cool down, atoms first form, the light is free to go, so we show that part of this photosphere around us that we could see is the cosmic microwave background. The universe at that point, there's very little structure formed, but the seeds are there, stars haven't formed, it's dark, the dark ages, and so on. And the CMB, cosmic microwave background, we can learn all sorts of stuff. So first off, inflation. We really would love to learn about inflation, and I'll go through that a little bit. We can measure the fluctuations, see if there's at the right spectrum, do they have the right correlations. And the thing you probably have heard about is we'd like to see all generic models of inflation predict that you will have not just fluctuations in the inflaton that led to these seeds of structure I showed you, but actually there should be fluctuations in the metric itself, or you should see tensor variations, or what you're used to hearing is gravitational waves. And those will cause a polarization in the CMB called B-mode polarization. So we'd like to look for that. It might not be there, or it might be at a level too low to measure. Then recombination, that's kind of where we see all those acoustic oscillations. We can learn about the dynamics of the gas. That allows us to figure out, how much dark matter, how much baryons, how many light relativistic species, how many neutrinos, right? We have this thermal bath, so we can work on that. We can, and I won't talk any more about it in today's talk, but when the universe reionizes, then you now have Thomson scattering of the light from the electrons, and that'll put an imprint. Very subtle, but an imprint on the cosmic microwave background. We can measure that and learn about reionization. It turns out we can do this thing that the light comes to us, but it gets deflected by matter, and this beautiful Gaussian fluctuations, quantum fluctuations, that should be uncorrelated get correlated because they've all been disturbed together by gravitational lensing. We can actually untangle that and measure that, and then we can start learning about how structure formed. And then lastly, we can learn about cosmic acceleration, this idea that the universe is accelerating again, because that affects very strongly how much structure we formed recently. And we can trace that through galaxy clusters, and I'll mention that. So a lot of jargon, maybe. For a physicist, here's another view. We want to look early on. We're trying to understand our universe. Inflation, we're talking about something like 10 to the 16 GeV for an energy density, trillion times higher than the LHC, right? At a time of something like 10 to minus 35 seconds. We don't know if that's right, but that's the area. Very exciting. Cosmic neutrino background, they decoupled at about a second, right? And so we'll mention this. So there are roughly every second a trillion cosmic neutrino background particles going through you per second. No one knows how to detect them. We see it in the cosmic microwave background. We can indirectly detect them. And then, of course, our messenger is here at a few 100,000 years, the cosmic microwave background, when the photons decoupled. So more on observations. There's Kobe, again, just showing in a different false color with the galaxy subtracted. WMAP went up and did a better job and mapped the whole sky. Planck went up and did a better job, again mapped the whole sky. And you can see we're just getting a more and more detailed picture, right? And if you pick your favorite hot and cold spots, you can see they get resolved. Yeah?
So some of those instruments you showed earlier were obviously not measuring the whole sky.
That's correct.
And when you do that, I mean, were the things that, I assume that was kind of the first thing, and then when you had something like Planck that measures the whole sky and high resolution, are those always confirming what you saw when you saw patches?
Yes,
or?
I'll show you more of that.
Okay.
That's a good question. The answer is yes. And so what I want to tell you is this is now what I want to more talk about is these two. So Lyman Page is got this going. It's called ACT. Unfortunately, you can't see it. It's in this little thing that protects it from seeing the mountains and stuff. It's a 6-meter telescope with this focal plane here. And this is the South Pole telescope. It's 10 meters in its focal plane. These are the workhorses that have been taking and going to much higher resolution from Planck even. In fact, much, much higher, but not doing the whole sky. And we'll show you how that fits in. So the South Pole telescope, that's my telescope, or my collaboration. Don't call it a satellite dish. Don't call it, it's a very high, precise, high-tech 10-meter telescope. It's got a 20-micron surface or better. It's a carbon fiber, complete truss structure. It's a really beautiful telescope. This here is this cabin where all the cryogenically cooled receivers, secondaries even cooled, is all in there. This can swing around and dock itself above the roof. The roof slides out, and that's how we have access to everything. It's pretty, it's beautiful. It has 1 arc-minute resolution, which is kind of neat. That means that we can resolve the microwave sky with this telescope at the same resolution your eye resolves light. Right? So if you want to get a sense for how detailed we are, that's about what it is. The first receiver we put on it was I don't know if it was the first, if it wasn't the very first, it was right there within months of the very first, what's called a transition edge sensor array. And that's what we started with. I'll show you more about that in a second. 3 bands kind of straddling that black body and using windows where the atmosphere is transparent. We replaced that with a polarimeter. I'll show you some of those results a few years ago. Just 2 bands, but now with polarization. And what we're building up to do is, and I'll show you more about this too, is to go to 16,000 detectors with this polarimeter and 3 bands at the end of this year. So this was order of magnitude advance, and we're going another order of magnitude. And at the end of the talk, hopefully I have time to tell you about what we're trying to do with Lyman, with all these other projects, to go yet another, from here almost 2 orders of magnitude, and to get at some of the science. Here's just a close-up to show you that dish there, and some of the team down there, just to give you a sense of, there is a reflector in there. But we'll go.
Do you have adaptive optics behind this?
No, we didn't want to have to deal with that in the cold, and that's why we have a carbon fiber. At this diameter and the precision we wanted, you can't do it with steel or aluminum. It will deflect too much from gravity. You'd have to be active. But with carbon fiber, you can do it. So we're 1 kilometer. The geographic South Pole is right there. This is the National Science Foundation Center. This is their junkyards. And here we are. BICEP you've heard about, we share with them. Keck is there. It's where Daisy used to be. IceCube, all their neutrino detectors are all buried in the ice here. This is where all the cables come out. So it's all right there, very middle of the, on the spin axis, on this high plateau. And the reason we're there is it's microwaves. You know, you want to heat up your coffee, you put it in a microwave oven. Water vapor is bad news. And it's not so much that we absorb a little, it's that it emits. You know, good absorber is a good emitter, so the atmosphere is emitting if it has water vapor, and it's emitting at a fairly warm temperature, and that's a lot of noise for us. So you want a place that's very dry, and then you also want a place where the atmosphere is stable. So we're up, we're at 10,500 feet. It's driest desert on Earth. And it turns out that the sun, which also is a big source of microwaves, goes behind the Earth for 6 months straight, you know, overnight, but it's a long night. And it gets incredibly calm. You know, you hear about storms in Antarctica, they're at the coast. At the center of the continent, it's very, very benign. So it just gets incredibly stable. In fact, we went just for being dry, but the stability is what really has been so exceptional about working there. Also, it has this unique geographical location that we can look out through the universe at one spot to really go deep, really drill deep, 24/7, 52, right? It's always up. Sources don't rise or set, so we can go very, very deep. And then, of course, there's a National Science Foundation that runs a station. So, you know, there's...
Why is the South Pole better than the North Pole?
Well, a few reasons. One,
Is it that
there's no continent, so the North Pole is wet. So there's nothing like it. A site that we're looking at for this next generation to add, to get more coverage, is the center of Greenland. Greenland's not, we don't have the statistics yet on the site testing. It looks pretty good, not as good as the South Pole. And another site we're looking at is Tibet. But the North Pole would be terrible. It's wet. So this is the collaboration, and I won't point everyone out. I just want to point out that there's a lot of institutions involved. We now have some funding from the Department of Energy, especially on the new camera. NSF, the Moore Foundation, Kavli Foundation have helped out. And looking at the weather today, you might not believe it, but we're having a collaboration meeting right now. It's ending right now today for the last few days. This is yesterday in Chicago, so amazing. A lot of great people, young people too. So one unique thing about the pole, well, there's many unique things, but one thing in particular is that we run everything remotely. We try to make things robust, but we're not just for 9 months a year when you can't get in or out of the South Pole, we have to leave someone there. And so we have what we call our winter rovers, or our heroes. And every year we hire 2 people who, when we take the last plane out in early February, they stay and catch the next one. They spend the night and get out at the end of October or so. So they really are heroes. And the amazing thing to me, and I always like to show this whenever I'm talking, because I always think there might be our next perfect winner over in the audience. So if you want to do this, let me know. But look at this, Dana Rubes, 2008, Dana Rubes, 2013, Dana Rubes and Daniel, 2010 and 2011. So people just love it. They go down there. It's like 40 or 50 people for the winter. And of course, we love it when people love to do it. But if you're interested, let me know. But I always like to highlight these people because without them, we'd be sunk. They're great. So let me say a little bit about the technology. And I'm probably going to run too late. But this was our first array. And so this was the first time at these wavelengths we were really building monolithic arrays on silicon and using these transition edge sensors. So we start out here. This is a very simple one where we have just a horn array sitting here. This is all of our readout, multiplexing readout. But here's the silicon. And you can't quite make it out, but every one of these little spots here is blowing up. So here's about 3 millimeters. And this is a silicon nitride mesh that's been released. It's only in contact with the whole rest of the wafer through these thin legs. Then it has a very thin gold film on it, so it's resistive and it absorbs microwaves. So it's just absorbing. So we have this thing sitting there behind the feed horn. As we scan our telescope, it's trying to come to equilibrium with the radiation on it. And on the middle of this thing, there's a little gold just to give some heat capacity, to tune the heat capacity. And there's a sensor, transition edge sensor. And this is the trick. This is what's allowed us to make these very, very quiet detectors. And of course, it's all made in a clean room. And so the idea is that you've got this absorber, and you heat it up, and you put this sensor on it. And the sensor is a transition edge. So it's a superconductor. You can tune them with a bilayer. And the idea is that this is the resistance versus temperature. And so it's normal, but you bias it in its transition. You voltage bias it, right? So it's sitting there at a voltage. And if it heats up, then you want to drive it warmer. The resistance goes up, and the current, to keep it in voltage, goes down. And vice versa. So it's very stiff. You can get high loop gain, negative electrothermal feedback. So you can just sit there in the bias, and you just monitor the current, and it tells you the incident power. Right? This is kind of the breakthrough. We can make these very quiet. In fact, make the detector so quiet that its noise it contributes is less than the noise you get from the atmosphere and the signal itself. So once you've done that, you want to figure out how to make many detectors. You have what's called background limited detectors. And the thing about this, of course, is that we can make many detectors, right? I showed you that wedge.
How big are they?
They have to match the wavelength. So the mesh is about 3 millimeters, but the actual TES sensor is of order 10 to 20 microns and tens of nanometers thick, right? So we make them. Here's how far the field has come. So this is now not 4-inch, but we're doing 6-inch. And we decided to take all those elements and now put it on chip. So instead of having just an absorber, we have antennas. This funny looking thing is an antenna, 2 polarizations. And then we can come off on superconducting lines. Our lines have filters, so we can filter into the bands we want. We don't have to put quasi-optical mesh filters in front anymore. And then all of our suspended TES detectors. So now we have for each pixel 6 bands, right? 6 sensors. And not just one person doing it, but teams of people. This is done at Argonne. And so this is what one of these wafers now looks like. So this is what's driving the technology and allowing us to make all this progress. So we get this on the telescope. This is yet to go on, but what's on there? We just flew back and forth. All these, in this case, thousands of detectors are sitting there, heating up and cooling off, but we're measuring with the TESs, and we record that data and slowly build up maps. So here is a map, right? So now we're not looking at the whole sky. We're looking at 1/16 of the sky, but at high resolution, an arc minute, 3 different bands, and that's what it looks like. And let me show you, I forget who asked the question, but we'll start now. This is 2,500 square degrees, and it's arc minute resolution, so you can't see the details. So I'm just going to show you 50 square degrees, 1/50th of this. And I'll start with WMAP, right? So this is WMAP, but only 50 square degrees, about the size of your palm held out, right? That's what it looks like. And then we go to Planck, right? And you can see, I forget who was asking, you see the same structures. And then we go to SPT, and then you could see it's resolved further. So a couple of cool things. One is you see the structure that's kind of cloud-like, lofty, cumulus-looking things. It's not really resolving, right? And that's actually because most of the power is in that degree scale peak in that power spectrum. But then you see all sorts of other stuff starting to come up, right? So if you take, let's say in this case, WMAP, and here's where we are in WMAP, as you said, space has, the whole sky, but on the ground you do these very deep and targeted fields and use, today's technology. If we take these things and then transform it, right, to make it in this spherical harmonic basis, that's what you get, right? So remember I showed you that picture from what was maybe 10 years before this, where there's lots of noise. These are with their error bars, and you can see these peaks coming out. You don't need the line to guide you anymore. But the amazing thing is the same line, there's slight parameter changes, but the same line fits. We actually go much farther than this. We can go out to about 10,000 in multipole. That's equivalent to about an arc-minute scale. And what happens is when you get out to about here, which is about a 4 arc-minutes or so resolution, then you start seeing all sorts of other things in the universe. They start dominating. And very interesting things. The reionization signal is in there. The cluster signal, which I'll talk about a little bit. All sorts of stuff is in there. But this primary CMB is at these larger scales. And the reason why is it's damped. It just keeps going down. And the reason these, I should say, these are at different frequencies, but all plotted for the equivalent black body temperature they would have. So once you're on a 3-degree background, they should line on top, but once you're seeing other foregrounds, they fall apart. Different frequencies separate. Anyway, let's go back just to this kind of primary signal. So this is now, that was, anyway, let me go on. So this is now Planck at, which Lyman runs, and SPT showing them. So it's pretty amazing, right? This now has the line that is more or less the prediction from this inflationary, dark energy dominated, cold dark matter model for the universe. And it fits beautiful, and it allows you then to solve for all these parameters. It's fit with only 6 parameters, right? So you could say, we're done. End of talk, just go home and, find a new job. But here's where we are. First of all, here's where we are cosmic variance limited. We really, in temperature alone, we're going to talk a lot about polarization, we really can't do any better. Unless there's something wrong with the data, we can't do any better, because there's only one sky to measure. So these big error bars down here, that's cosmic variance. There aren't a lot of samples, right? Get to many, many degrees, aren't that many on the sky. Going on, though, we could definitely improve on the other side of that. Also, one thing about this cosmic variance limit is, notice this weird feature. That was in WMAP, that's in Planck, that's real. And some people make a lot of, they say there's something new, there's other people say that's just a fluke. But it's there, it's on the sky. Anyway, that can be improved. And when you get out here, where I showed you where we have SPT, we've only measured 10% of the sky. We can do a lot more improvement. And when you add polarization, you can do a lot more as well. So obviously we can make better measurements, but would it help us? So already we know from solving the dynamics, we know things like baryon, B baryon, or just ordinary matter, right? You all know this. Everything we know about and can label and put in our textbooks is only 4% of the energy density in the universe, right? So there's a lot of dark stuff we don't know. But we have this chart. It's cool. Dark matter, we know what it is. And the neat thing is there's no way, we're looking at this stuff in a plasma. There's no way that the dark matter we're seeing is just ordinary matter that's in old stars or just black and not interacting, machos or something. It's some other particle that does not interact. So it's new physics. And the difference between these is not a couple sigma. It's the fact that it's updated. It's more like 50 sigma, right? So there's no way we're just getting it wrong. So this looks great. But if you want to go beyond this model, say, okay, let's add mass for neutrinos. Let's say maybe there are other relativistic species. Maybe the model we're using is incomplete. Then those models are poorly constrained. And the way to do better is to add polarization data. Right? What about inflation? Right? So first I keep saying this model is an inflationary model. So inflation says that geometry has to be flat. On the last view graph I didn't mention it, but it says that we've measured it to better than 1%, better than 0.5%. You have these superhorizon features, which I talked about, this harmonic series of peaks. The fluctuations, we look at the statistics, they're just adiabatic and Gaussian, they all fit. And a cool thing that's come out in the last few years is that inflation, you're in this model, you've got some hyperexpansion going on because, Friedman equation, you're whisking things out of the horizon. It's a scale invariant process. So the fluctuation spectrum you end up with ought to be scale invariant. But inflation has to end. It has to slow down and end, which means we should see some slight departure from scale invariance. It's a prediction of inflation. And that's now been measured, which I think is cool. So the other thing is, and I mentioned this earlier, is inflation would predict you'd have metric perturbations. So you'd have some sort of fluctuations in the metric or gravitational waves. And that will will produce some power, and we should be able to see that. So it turns out that gravitational waves, if they're just coming out in the horizon, they just decay. So once they come out and start to evolve, they decay. So we're only going to see them at very large angular scales. But that's, if you remember, that's where we don't have the best data. There's just not enough modes to measure. So we can only get to a certain limit measuring the temperature. So let me show you where that is. This is this scalar to tensor ratio, or the, whatever you want to call it, R, but the level of the normal fluctuation, gravitational disturbances to just the scalar, just the density ones. And this is this tilt or spectrum of the fluctuations when we fit. One being scale invariant, right? So we don't see it. It's not scale invariant, and it's heavily ruled out. And we have this limit to what the tensor to scalar ratio can be, and we can't do any better with the temperature data. We're set by the sample variance, right? So we need polarization data to prove that. So the other thing is, if you think of, here's this plot you see all the time, the dark sector. That's today. But, we're looking back and we're measuring things at a redshift of 1,000, almost 14 billion years ago. A lot of expansion has happened, and so the different species evolve differently. If it's just cold and pressureless, then it's going as 1 over the scale factor cubed. But if it's relativistic, then you're also stretching the wavelengths, and the energy density is going as 1 as the scale factor to the 4th power. So this is what it was at a redshift of 1,000. And you can see neutrinos, and this is, of course, what we're measuring. Neutrinos and photons, of course, are very important. And if the neutrinos have even a little mass, there's so many of them, they will be contributing actually even to this dark matter. In fact, with the minimum mass for neutrinos, which we know from the oscillation experiments, the neutrinos in the universe give a mass equal to all the stars. There are a lot of neutrinos. And they were talking, the minimum mass means the sum of the 3 neutrino species is 60, 58 or whatever milli-eV. Very little, but there are a lot, right? So we can analyze this data, and I don't want to go through the details, but we can analyze the data I've been showing you to try to constrict how many relativistic species there are. And there's a very firm prediction if there's just 3 values of neutrinos, and the mass. So this is a plot using all the data from a Planck paper showing this quantity NF. So NF is this effective number of relativistic species, light relativistic species. And the theory, for standard cosmology theory, 3 neutrinos, right, the gammas, the photons are out, is it should be 3.046. Because it's not perfect thermal equilibrium. You have an electron, positron annihilation, you mess up the spectrum a little bit, and so you get this funny 046. Right? This is the constraints from the CMB data. So the neat thing for me about this is 0 is nowhere on this scale, right? That we're seeing with like 10 sigma confidence the impact of the cosmic neutrinos. We can't fit our models without them. It's not the same as saying we detected the cosmic neutrinos, because you got one in your detector, but we need to know them. At the same time, we get a limit on the total masses. And if you use just the CMB data, since we're looking at this high redshift, the universe kind of energy density is about EV, so you can't really do better. If you use more local data, and in the future CMB lensing data, you can drive this down. But right now, these are the best limits on the mass of the neutrinos. Some of the masses. We don't measure any individual one, but the sum of the species. Pretty neat. Yeah.
I probably missed this, but what about your measurements gives you an effective? What is
So
the thing you measure?
I took out those view graphs because it takes a while. But basically, we could solve for the energy density of the universe at the time of decoupling. In fact, we do even better. We can measure the sound crossing, we measure a damping scale, And those two combined, their ratio goes as the square root of time. One is a diffusion, one is just expansion. So we can actually solve for Friedmann's equation for the energy density. And then we've measured the gammas, we measure the matter, so you do the math and you get this. Okay, so I'm going to move on a little bit, and I'll probably have to watch the clock. The other thing, so we're coming closer to us now, is I mentioned this in the beginning. When we look at the CMB, we're looking, of course, this light has traveled across the universe to get us. There's structure that is formed in the universe in the meantime, and gravitational lensing. That is, the photons on average, when we receive them, on average they've been deflected about 2.5 arc minutes, right? So, and by large-scale structure. So here's a little simulation. This is just a simulation of what the projected, lensing potential. Just think of this as the projected mass in the universe. And this is the CMB, just a simulation. But that's the CMB before it's lensed. So look carefully, and you can see as I go to the next page, it changes. So you say, okay, what the hell are you going to do with that? All right. Well, there's smart people in the world, and if it's lensed, then you, especially if it's lensed by large-scale features, you've taken small-scale things and correlated on large scales. You introduced all sorts of correlations into this, what was a nice Gaussian, completely independent mode. You've coupled them. And so you have the covariance, and you can solve it, and you can actually go from here and solve for what that was. Right? And if you want, you can unlens it. But you can solve for that field. And Wayne Hu worked this out, 15 years ago now, but it's only recently we've had the data to be able to do it. So that's that map I showed you. We take that map, 2,500 square degrees, and make this map. And this map is really cool. What we're looking at is all the projected matter in the universe in that part of the sky. That's what it looks like. Right? So we have that, and of course that's going to be very sensitive to how structure formed and all sorts of other things. And to show you that it actually works, this is just where we have a particularly deep patch, 100 square degrees. And the contours, of course you want positive and negative, is this projected kind of potential or mass. And the grayscale underneath it is taking infrared galaxy densities. So basically weighting the galaxies by about redshift 1 or 2, just measuring it from a space telescope. And you can see that they correlate. They shouldn't correlate perfectly because the line of sights are a little different, but they correlate extremely well. And it turns out this is a tool which we're now using with the DES, Dark Energy Survey. It's a big feature going forward with LSST and all these other surveys to help calibrate the mass. Because we have this, we know exactly where our source screen is. Redshift of, exact redshift, we know its properties, we know its statistics. And so we get these very accurate mass maps. So that's, you're going to hear a lot more about that in the future. And let me show you. You can take this. We always do this. Whenever we have a map, we transform, get spherical harmonics again. And you get a spectrum like this, which is cool. This is the projected matter, but the power spectrum, the YLMs again. And one reason this is nice is that if neutrinos are contributing to the matter, they're still pretty hot, unless they're really heavy. But if they're just a couple tenths of an eV or less, what they do is they contribute to the matter, but they don't clump up. They actually suppress the formation of structures on smaller scales. They change the matter power spectrum that you would observe. So it turns out this curve is not good enough to do it yet, to help a lot yet, but eventually we can measure this real well. We'll be able to measure the neutrino mass by how it affects the growth of structure. And to do that well, we need polarization. Everything needs polarization. That's the theme of this talk. So let me come back to this map. I think it's a little saturated here. This is, remember, just this small patch, 1/50th of the sky we mapped. And I want to talk about what else is in it, right? So let's filter out the CMB. Took years and years to measure it, but now it's a nuisance. So we filter out the large scale, right? And then you can see, there's still CMB showing up. That's that fine scale stuff. But then there's other stuff. So these things are unresolved bright sources. For the most part, these are active galactic nuclei, those sources in the middle of galaxies putting out all sorts of energy, and people have been studying it for decades. But, you know, we have 3 bands. We can measure the spectrum, and it turns out that some of them are not. Some of them are really totally different spectra, and it turns out they're dust. It's like star formation. They're dust, hot dust, dust that's around where stars are forming. Stars go off, they get heated up, and the dust re-radiates at long wavelengths. And you can tell that by the spectrum. And they're all, it took forever to find them. Actually, it's with ALMA that we find them. They're at high redshift. And it turns out that what they are is they're gravitational lensed. We expected to see none had ever really been detected. But at this resolution and these kind of wavelengths, people before these experiments had only surveyed 1 square degree of the sky. It turns out there's about 1 every 10 square degrees. So these are kind of neat. So that image there I'll explain here. It was an optical image. So we see the foreground galaxy, big elliptical, galaxies. But we see these backgrounds being lensed, right? Gravitational lensing again. So the image we get is something like that, where the red is what we see in the dust from ALMA, and the white here is what we see in the optical. It's a composite image.
Which is the thing that you see in the CMB?
So what we see in the CMB is the dust, but we don't resolve it. This is an arc minute resolution, or 60 arc seconds.
From the guy behind?
We don't see any of the optical. And when you look in the optical, you don't see any of the dust. We have hundreds of these now. We have not found any in the optical emission.
So these dots are the actual, those are the ones that are lensed. It's just that you can't resolve it there.
Right, so we didn't know what they were. We just knew they were dusty. And if they weren't lensed, they were in no other catalogs. Mm-hmm. Right? So it turns out they're very high redshift. So you go to ALMA, these things are the brightest point sources in the millimeter sky. They're just very rare, right? So you go to ALMA and seconds. You only need seconds. Almost this, no doubt you heard about this in earlier sessions. And then you image them with ALMA, and what you get is, all these Einstein-type rings and all this stuff, which is really cool. The coolest thing about this, from my perspective, I mean, people love it for studying star formation in the early universe and that. But there's a big, you probably heard this, that there's a problem with dark matter models. You get to small scales, not enough satellites around the galaxy. We can look with ALMA, this incredible resolution, we can go look and measure now the substructure around these big elliptical galaxies. And we're doing that. We have our first paper out on that. So we should be able to, in the next couple of years, be able to tell if we get the right statistics for these things. So total surprise, but I thought I'd mention it. The other thing is we couldn't ever get redshifts for these things because you can't find them in the optical, but once you get to ALMA, you can just look in the millimeter lines. They're so bright, you just need a minute or two of the spectrometer. You don't have a big wide spectrometer, but you just step it along, and then you can see them. And we're finding redshifts. The lowest redshift is like 2. There's none close to us because they're lensed. And our record now is 6.9, which is, for those who know about epic ionization, is pretty interesting redshift. So the other thing, though, and actually this is why we built the instrument to have the resolution it did, was to try to find these little dark spots. Right? And these dark spots are caused from very hot ionized gas scattering photons out of our line of sight by galaxy clusters. Right? So a galaxy cluster, they're beautiful images of all these galaxies, thousands, sometimes 10,000 galaxies. But the galaxies are just trace particles in them. They're really just these very deep potential wells of dark matter. And they're so deep that if you were to drop a nucleon in, it would thermalize at 10 to the 8th Kelvin or so. So even iron is ionized. So you get this huge mass of ionized gas. And these are the largest structures the universe has produced, right? And how fast they form, when they form, is really sensitive on the expansion history of the universe, and on gravity, of course. So it's a great way, if you can go find all these things, when they formed, what rate they formed, it's a great dark energy probe. It's a good way to test dark energy and growth of structure. The problem is trying to find them. So this is a galaxy cluster with the X-ray emitting plasma, which is where almost all the baryons are, not in the galaxies. And if we turn off the optical and just leave the X-ray on, then you could see it's this very diffuse, hot atmosphere. And there's this effect, right? So if you have your little photon, CMB photon coming in, it will scatter, and that's called the SC effect. And the net result is basically it's a very small chance of scattering. It tends to scatter photons out of your line of sight, and you just see a decrement, right? And you get this funny pattern. If you say, what is it compared to the background? It's a decrement, and of course you get a pile up at higher frequencies. This is the amplitude of the signal versus frequency. So there's a couple cool things. One is you're just measuring the number of scatterers weighted by their temperature. That's pressure. That's depth of the well. That's a very good mass proxy. The effect you're measuring is a shadow. If you can detect it at any distance from you, you can detect it at all distances. So now that we can detect these things, we can make an inventory of all of them. You just have to go find them and get redshifts. And then there's this other funny effect, which is that if this galaxy cluster is moving relative to the cosmic microwave background, that whole gas is like a moving mirror, then you get another effect called the kinematic SC effect. And so a cool thing about this is we haven't really measured peculiar velocities, but we can show you that a galaxy cluster, which appears to be moving close to the speed of light away from us, is not moving relative to the cosmic microwave background. And neither are we. So you can show that it's the space that's expanding, not moving through space. It's kind of fun. Anyway, so we've done this experiment, and we have a limit to the mass we can see, but we can measure all these galaxy clusters, just taking an inventory. And so what we have then is the reason we don't see galaxy clusters this high mass and this far away is because they don't exist. It's not a sensitivity issue. They haven't formed. Right? So we're just seeing evolution in the universe. So if you take that plot and try to fit it, so the kind of number per dn dz, or the number per redshift bin, that's our fit. This is basically the prediction from lambda CDM, this model we keep talking about. And it looks pretty good, but in fact, it doesn't quite fit. It wants, when we do this, it wants us to have a little more mass for neutrinos. So this is we need to do better mass calibration, but this is an area that's interesting. There's lots of ways to get at this neutrino mass, and this is one of them. And of course, what we really want to get at is, well, it wants around a tenth or so an EV for the sum of the masses. So polarization, and I'm probably really running late, but I'll try to be fast. Let me just say that we're looking at the surface of last scattering. Scattering is polarized, right? And so you have this T, that's what we measured. You have this what's called E mode, or just polarization, power spectrum, and that's fixed. You measure one curve, you can predict the other. That's just last scattering statistics. If there are gravitational waves, you will produce a little E, but you also produce what's called B mode. The gravitational waves can allow you to get a curl across the sky, right? And this is, of course, the holy grail that lots of people are looking for. And this level that I've drawn it there is a little higher than the level that's now been ruled out, but it's comparable, right? And that's at a level of, this is 0.1, that's about the limit right now. That's an energy scale of inflation, 2 times 10 to the 16, 0.01, et cetera. So it drops quickly. And so, but the recipe is clear. Go out, make a map of the sky, get a vector field, and have a divergence-free and curl-free component. The divergence-free is going to look, the divergence component is going to look just like this, and you'll see that. And the curl-free, you can read off the energy scale of inflation. Great. It's not so easy, of course. One is that this beautiful vector field, which was generated at the source last scattering, got disturbed on the way to us. So it actually gets a little of this curl-like component and pollutes things. And then there's foregrounds. So we've been doing that. I'll mention the 2.5 meter polar bear telescope. You guys must have heard the name BICEP 2 at some point in the last year or two. They're just targeting these real large scales. Spider, I know that there is a talk this week or next week from Spider. They had a very successful balloon, kind of like BICEP, looking at large scales. They're not releasing their data yet. Others are looking for this, and so that's happening, and so we're doing that. But let me show you the first detection of B-mode polarization, although it was not the inflationary one. And that is, we took our E-mode map, the polarization of the E-modes which we measured. We took a lensing potential. We could do that from our lensing map, or we could do it from the infrared data I showed you. And then what took the universe 14 billion years to do, we do in a computer. We produce what the distorted spectrum would look like. And now we have a template. This is what the B-modes in our map should look like. And so we can correlate that with our maps, and we get a detection. Right? So that was the first. The reason I like to show that is because this process in reverse is how we want to clean up that signal. We can predict it. From the measuring the E-modes, measuring the gravitational lensing, we can predict the lensing B-mode signal and remove it. So we can get rid of that contaminant to some degree. So what has been happening with polarization? Here is all this data in the last 2.5 years, right? So it's really going crazy. In fact, this is a compilation made by Lyman Page. Here is yet to be released. This is our map, 500 square degrees. Same exact field on the sky as the BICEP data, so we can do this trick of measuring modes. To show you the signal to noise, here is the map made where every time we add data, we flip the signs. So the noise is all there, but the signal goes away, and that's like that. So it's very, very high signal to noise measurements. Here is the power spectrum of the E-mode today, and you can see these just tiny error bars. So lots of progress, right? Looks great. If we put all that data, combine it, not our newest data, then here's the E-modes, and you can see we're mapping that curve out. We're going to be able to do lensing. We're going to be able to do all these things I've been saying. And the B-modes, we're seeing that, and you say, well, geez, you've come 5 orders of magnitude, what's another 2? But we finally have gotten to the point where it's not so easy. So we've been in this mode in a temperature. So these are the Planck maps. We've been in this mode for years where you just pick the part of the sky which is pretty clear and you can manage foregrounds. You don't ignore them, but you can manage them. And there's lots of region, it's shown by this kind of bluish tinge here, where the CMB dominates, right? So it dominates at these frequencies near the peak of the CMB. Dust kills you at high frequencies, synchrotron at low frequencies. But it's pretty good. It's not at all the case when you get here. So for E-modes, for almost 90, E-modes are actually cleaner. The sky is cleaner for looking at E-modes than it is for the temperature. But for the B-modes, you're buried. You're totally buried. So you all know that BICEP had a measurement, beautiful measurement. This is just showing their map. The curl looked great, and it turned out to be dust, right? Or it's consistent with dust. They only have an upper limit, right? Their measurement, by the way, this is now taking the peak of where you would expect the measurement to be in that angular power plot. Their noise was at this incredibly low level, but the dust level is much higher. This plot's a little complicated. They had to figure it out working with Planck, but they saw dust. So the trick now is to figure out how to get around that. So you use many bands, and you have to use this delensing trick because you want to get below that other foreground. And this is just to give you a sense of where they are. So now they have a limit on this, R, energy scale of inflation, or this ratio of the tensor to scalar fluctuations, which is just below what's been done on temperature. So after all these years, the polarization is now forging ahead. And now we can delens. That is, we can use our high-resolution data and their data and actually try to delens it. So we expect, working together, we haven't, this is new, working together, get down in a couple of years to a level about 4 or 5 times lower than where they are now. But it's going to be very hard to go further. And all these things we want to do, neutrino mass, the lensing, the dark energy, galaxy clusters, we're saturating again. We've got to do more. So this is a plot, and I can wrap up in 2 minutes. Sorry, but this is a plot of the sensitivity of the field. It's just raw sensitivity showing the last 10, 20 years. You can actually trace this all the way back to Penzias and Wilson. And we've just been on this trajectory. And what I showed you earlier, going from 100 to 1,000, now to 16,000 detectors, and every time getting telescopes with systematics that can handle all that sensitivity, we think we can keep going. That's what we want to do. But we've saturated our focal planes. This next step will saturate them. So now we need many focal planes or telescopes. So the next step is we've got to bring the whole community together. And this is this project which some of you probably heard about called CMB-S4, or Stage 4. That's what we're doing, and we want to get of order 500,000 detectors. We want to get South Pole and Chile, and maybe a site in the north. I can go through some of this quickly. We've got the community together. We're having these workshops. The next one is actually very soon, in 2 weeks. Going. We've got right endorsements. We think we know how to do it. And this is the kind of levels we expect. So we'll get down, I think, to an R upper limit of 0.01. Still not enough to rule out all the kind of generic inflation models. We'd like to get to 10 to the minus 3, but this experiment will do it. We get down in this quantity where we can measure whether we understand neutrino physics in the early universe, in the neutrino background. We'll get down to that level with this experiment. We'll get down to a measurement through lensing of the neutrino mass, where we will have a definite detection of the mass, even if we're in the normal hierarchy and the minimum mass model. Right? So we'll get there. And I won't talk about dark energy. So that's what we're doing. Let me just show you. Chile you'll learn about. Here's a cute plot. Just to put it in perspective, this is right, 10 sigma detection, but that's where we're headed. I don't know if it'll be there, but that's the kind of uncertainty we're headed for. Clusters, 3G, the experiment we're building now is going to be great, but we'll get way down. And what's interesting here, and it's getting a little detailed for the astronomers, is that we will be able to use the lensing of the CMB to mass calibrate our galaxy clusters. So it'll become an extremely powerful dark energy probe at that point. So anyway, I just want to say that to end, thanks for letting me run long here, but it's been an incredible 50 years. It's not over yet. This model has emerged. It's hard to believe it's going to keep working, and we won't find any cracks, but if we don't, then we'll start learning more about neutrinos and other stuff as well. Who knows, but there's much to do, and I just want to say that the CMB just keeps delivering. So stay tuned. Anyway, thank you.
Thank you, John. That was a beautiful talk. And, don't you agree?
Yes.
We have time for questions. Yeah, John.
John, you talked about forgetting the beam modes, using multiple bands to better understand
The foreground,
dust,
yeah,
the
yeah,
foreground. There's experiments like Piper that are going into the sub-millimeter. Do you think it's important to go into that, or what bands do you think are the ones?
So this is a question that comes up, is that the CMB, the cosmic microwave background itself, from about 30 to maybe 300 gigahertz, straddling that peak is where you can get measurements of that. And does it help you to have channels much higher frequency, let's say, to understand the dust? And some people say you have to have it or you'll never understand the dust. And that's absolutely true. But to understand the dust well enough to know whether it's contaminating you or not, you also need to measure very close. You got to measure the spectrum through. So I think you want both. But I think if you didn't care about dust for dust's sake, then the highest frequencies are probably not that important, because you're going to have to just measure it very close. But Bruce Drew,
Go above 300 or not?
I don't know if you'd have to.
Okay.
If you had it, then you'd learn more about the dust, but would you
Okay.
be able to subtract it better? I don't know. Bruce Drain would argue the opposite. Alex Lazarian would argue the opposite, that you'd have to understand. So,
Good, yeah.
Simple physics question. When you do the de-lensing and you get that map of the projected mass density,
yeah.
What am I looking at mostly? In other words, which redshift contributes to
Oh, so what is the kind of the weight versus redshift? It climbs up. It climbs up and peaks. I don't have it handy, but it peaks up at about redshift 2 or so, and but it's very gentle, and then drops back down.
And that's just because that's the peak of structures going
Yeah,
on.
well, but also, of course, it needs to know where the source plane is to get the maximum lensing, and that's at redshift 1,000. So there's two effects. If it's too close to you, then you don't get a big effect, and you want it about midway to your source plane. But you have to also wait for the structure to grow. So, but clearly, it's not matched directly to the cosmic infrared background.
Any other questions? So are there any plans for satellites or missions?
So there's a satellite. There's lots of thinking. There is a satellite plan that's kind of very, small scale, kind of like a bicep in space type idea called Lightbird. It's led by the Japanese, and they're still working on defining it, but they've got a pass on phase A, so they have phase A money, and it would be kind of degree angular scale, but lots of frequencies, all sky. And they're claiming that they can get to about a 10 to minus 3 for R. But once you go to space and you're limited in resolution, then you have to do that by doing that very, very low L, what's called the reionization peak, because you can't de-lens. You don't have the data to de-lens. So it's very complementary.
All right, very good. Well, thanks again. And as I mentioned before, today is John's birthday, and I actually ordered a candle, but somehow they didn't bring me a candle. Just
After lunch.
Yeah, please, happy birthday.
Thank you.
And we have some cupcakes and pizza. Please take your seat.
All right, well, thank you all.